So our next question involves looking at splitting patterns for proton NMR. And so we can just start anywhere we want within the molecule, but remember it's really just a matter of finding the neighboring protons. And so where could we start that might be the most straightforward? Probably up at the top. So here we have a CH3 that is adjacent to two hydrogens. If it's adjacent to two hydrogens, we'll get 2 + 1 or a triplet. Moving over to that CH2, this CH2 is adjacent to the methyl group, which gives us 3 + 1, but it's also adjacent to these two, which is 2 + 1. We can't sum those together because the 2 and the 3 are not equivalent to each other. So we get 3 + 1 as well as 2 + 1, or 4 × 3, for a total of 12 peaks. The next one over is a CH2. It's also adjacent to 2, which makes it a triplet. This carbon here, these protons are not adjacent to anything. If it's not adjacent to anything, then we have a singlet. All right, going down to the aromatic ring, that proton on the aromatic ring is adjacent to one proton, which makes it a doublet. This carbon here is adjacent to just the two hydrogens here. 2 + 1 is triplet. Next, we have these hydrogens, which are adjacent to the two here, which is 2 + 1, but is also adjacent to this one here for 1 + 1, or a total of 6 peaks. Here we have this methyl, which is adjacent to one hydrogen, which makes it a doublet. And finally, I skipped over this one for a moment because it's the most complicated, but it's adjacent to these two, which gives us 2 + 1. It's also adjacent to these two methyl groups. But are these two methyl groups equivalent to each other? The answer is yes, which means that we can then add those together for 6 + 1, and we get a total of 21 peaks here.